want to welcome everybody here. Thanks. And I've been sort of introducing people to people, and we'll introduce more people to more people as the meeting progresses. And I've prepared a very modest couple of slides to talk about what we're going to talk about. And if I press the right button that says share instead of leave, there we go. Okay. We're always talking about adding common sense to AI, but today what I wanted to do was a quick overview of what we've done and how the software works and what the current state of the software is. Then we'll dive a little more into vision. I devoted the entire last meeting to vision, and so I'm just going to talk a little bit about how we've how the project has progressed in the intervening month. And then we're going to talk about the big topic, which is language, and the problem of language being that it is ambiguous, where human thought is much less ambiguous. So, starting on the question of common sense, I see three necessary components to common sense. And the first is you have to have the knowledge storage and the ability to infer information from other information that you've received. You need to have some senses and interaction with a real world. And it struck me as I wrote this slide that if you were to build a common sense or perhaps a conscious entity, there's no requirement that the real world be the same real world we have. It can be a simulated real world, and everything might still work. And I thought that was a very interesting thought. But you do have to have an internal mental model that allows you to simulate a future of trying out different events, different actions and seeing which ones work. And it is clear to me that these three things are necessary. The question is, are they sufficient? And to answer that question, my pragmatic approach is to build them and to see what doesn't work after you build them. And then you get to extend the list. People with a more theoretical approach might want to go down this road of looking at what it is that, right now, what are all of the components of common sense and understanding that you need. But being a pragmatic sort of a guy, I'm happy to work on these three, but it doesn't mean I'm not interested in talking about what the other items are. So, what's the Brain Simulator 3, and how does it relate to the Brain Simulator 2? Brain Simulator 3 is the current software project, and its intent is to be able to know anything a human mind can know and to do anything a human mind can do. Now, I know this is a pretty tall order, so as we move forward, you'll be seeing how these are cut down into some smaller pieces. Brain Simulator 2 is a precursor to Brain Simulator 3. It was neuron-based, and it would handle up to 1 billion neurons of various models. And from that, I learned what it is that neurons are really good at and what it is that neurons are not so good at. And Brain Simulator 3 is an outgrowth of what Brain Simulator 2 could do, but it is graph-based. That is, rather than having a lot of neurons, I verified that I can build this graph in neurons, and then I say, I don't need the neurons anymore. Let's just work with the graph. And so the graph that we have it's a combination of a collection of nodes and edges, and it is biologically plausible to the extent that I can create a similar graph in neurons, and the neurons models that we have are biologically plausible. So we've taken a pretty big level of abstraction away from what neurons themselves do, but with a little imagination, we could say that's still pretty biologically plausible. So what's in Brain Simulator 3? First, there's this major component of storage, which is the Universal Knowledge Store, or UKS. Then there are a whole suite of agents, and you can add new agents to do things. And these agents, some of them talk only to the UKS, and some of them also talk to the outside world. And so I'll be talking about what does the UKS do, and then what are the agents that we currently have, and what could they be doing that they are, what are we doing to move forward with them? So Universal Knowledge Store is a graph, which is in mathematics is a collection of nodes connected by edges. And within the brain simulator and the UKS, I call nodes things and edges relationships. So when I use the word relationship with a capital R, that is a specific item within the UKS, as is things with a capital T. So within the UKS, everything is a thing, and all of the knowledge is relationships that connect things to one another, and I'll get put into some details in a moment. There are a number of features that are inherent in the UKS, of which one of the foremost is it handles attribute inheritance with exceptions, and I'll demo that in a moment. Other things that are necessary include understanding that a relationship relates to things, and it has a relationship type. It also has a lot of other stuff like a confidence and a time to live and bidirectionality. But we have this picture here, and I don't know if you can see my mouse cursor, but this is how the UKS represents the idea that Fido is a dog. So Fido, it has this relationship, and the relation type is a, and it connects to dog. And Fido has fur. So again, there's a second relationship, and the relationship connects a source and a target, and it has a type. The source, target, and type are all things, and that means that there is no limitation on how many you can have or how they work together. ISA relationships are a little special in that they allow for attribute inheritance, but so too, there are other relationships that also do that. A clause, I'll talk about only very briefly, in the same way that a relationship relates two things to one another with a relationship type. A clause relates to relationships with a relationship type. So it sort of creates uber relationships. And it is my contention that with this simple structure, you can represent absolutely anything. I haven't proven that, but I think it is quite likely that with the nesting capability of clauses that essentially there's no limit, and nobody has yet shown me anything that I can represent, that I can think of that I can't represent in the UKS. And when somebody does, I will make an extension to the UKS so that we will be able to handle that. I'm not concerned. And before we move on to agents, I realize that I'm glossing over this very quickly, and I'm about to do a demo that will make things clearer, but are there any questions that I should be addressing that I've glossed over too much? Okay, moving on. So you have this setup, and you have this collection of agents. And the agents are little blocks of code, and you can make them as complicated or as simple as you want. But here is a sampling where of things that we could have, like attribute bubbling, where this is an agent that only talks to the UKS, and it looks for things that have common attributes, like Fido has 4 legs and Spot has 4 legs, and perhaps because they both have 4 legs, you could say that a dog has 4 legs, and that has suddenly compressed the, because you can then inherit that attribute, you don't have to store it in all these multiple places. You only have to store it once. Very similar to that is automatic subclassing, and that again looks for common attributes and says these things all have 4 legs. Perhaps they should be part of a common class like dogs or quadrupeds or whatever. The next one we're going to talk about, and I'll talk about this in greater detail, is vision. And vision takes sensory input from the outside world and it massages it into the UKS. And I'll demo how that works. Here's William's GPT interface that he's done for language and for other things. And it talks out to GPT and it gets information back and stashes it in the UKS. And you can easily imagine, of course, there are other robotic senses. And to me, one of the necessary requirements for a system to understand 3-dimensionality is to have mobility within a 3-dimensional world. Without any proof at all, I contend that if you cannot experience a 3-dimensional world, it is highly unlikely that you will ever understand that objects exist in 3 dimensions. And so the intent is to move forward with additional agents and perhaps some new features to the UKS, but the UKS runs at least reasonably reliably at this point. And so now I'm going to go over to a demo of the UKS, which will maybe give you a better idea of how it works internally. And here we have the BrainSimIII 3, and these dialog boxes are all associated with various agents. And this agent is the UKS display, and all it does is look at the UKS and display in a tree control some of the data that it finds. And this is an agent that will add data to the UKS. This is an agent that will query the UKS. This is an agent that will build clauses. And I'll demo each of these really briefly. I can say Fido is a dog. And you can see how the UKS just got modified in that it created a new node or thing named, which has a label of being dog. Remember, these labels are entirely arbitrary, and so this is just a label on a node. And although the system knows absolutely nothing about dogs at this point, it does know that Fido is one. And it knows that with some degree of confidence. And so we can say, well, we'll get back to confidence in a moment. Spot is a dog and Rover is a dog. And if we ask in the query box for the properties of Fido, it says, I don't know anything about Fido. And just to give it a property and to show how that displays, I can say Fido is brown. Now Fido has a relationship to by the way, it had to create a new node called brown and create the idea that Fido is one. And now if we requery, we'll find out that Fido is brown. To talk about inheritance, we can say dogs have tails. Now we have the relationship, and because of the indentation, it's a little hard to tell, but this relationship is related to the dog, and dog has a tail. But now if I query Fido, I'll see down here that Fido has a tail and is brown. And so that's how adding a relationship to a parent, that attribute is inherited. So we can say Spot only has a tail because he inherits it from dog, but we haven't said anything specific about Spot. But we can say dogs have 4 legs. And now we can query Spot, and Spot has 4 legs, as does Fido, as does anybody who inherits from dog. And I can say that Tripper, the problem is that you need exceptions because there are no hard and fast rules. And so if I look at Tripper's parameters, is he has 4 legs and a tail. But if I say that poor Tripper only has 3 legs, and now query for Tripper, I have misspelled Tripper. Did I get?
You put an S on one of them.
I did. Now, but it was only on the query that I did it wrong. So now Tripper has a tail and 3 legs because when you put in exceptional information, it overrides what it might otherwise inherit. And so this is an extension of what you might call a knowledge graph because it has this automatic inheritance. It has some other things that are really important, and I'll just turn on some of the details here. For every relationship, it has a confidence level. And so you can know things with varying degrees of confidence, and it defaults to putting things in at 0.9, but you could set it to anything you wanted. The infinity here is a time to live on the relationship. Although many things you learn you'd like to remember forever, there's a whole lot of things that you learn that you don't care about, like much of the content of what I'm saying will go through one ear and out the other, as it is you have to create all of these relationships in your brain in order to understand what's going on, but only the important ones will stay around, so you can set a time to live on any relationship. Every relationship also is stored in reverse, and so you can turn on or off reverse relationships. So here, if you wanted to query on what things are brown, you automatically have the relationship here that Fido is brown. And so you don't have to go very far because you can follow every relationship in reverse. You don't have to go very far to learn the reverse information. And it's very clear to me that the human brain must store reverse relationships like this. And the reason is that neurons are simply too slow to go searching around the way a database doesn't, a relational database doesn't need to store all of the reverse information, because it is so fast at searching that it can search without storing all of the reverse relationships. And so I've put in these reverse relationships because it impacts the way I think about how searching is going to happen. I want to show just what a clause does and how it extends your concept of what you can put in here. Dogs can play fetch if the weather is sunny. And under dog, it's put in this whole relationship. And if I look at the information of Tripper, Tripper can now play fetch. But if I come up here and give it more specific information, the weather is mist, not sunny. Now down here under weather, I have the information that weather is not sunny. And if I query Tripper again, Tripper can no longer play fetch because the weather is not sunny. And an interesting thing about this relationship is that neither of these, that the question of whether or not dog can play fetch is neither true nor false because it's conditional on other information. Okay, that's all I was going to say about the UKS. And let me just stop this for a moment and say, given that's the UKS, do you generally get the idea of the power of it and the kind of information that you can store in there? And essentially, any information is what you can store in there. And do you have any questions?
Yeah.
One question about multiple inheritance. Sorry, go ahead.
No, you go ahead, and I'll do it next.
Yeah, just so it's good, looks good so far. Two questions actually. One about multiple inheritance, and the other question about meta interface to let you know all the agents that are running. Maybe the agents can report to some segment of the UKS their status, and then you can report on that with a window.
Let me answer two questions, both questions. The first is in terms of multiple inheritance, the answer is yes. And a typical example of why you might want to use this is you might want to say that Heather is a woman, and from woman, she inherits a whole set of properties. And you might also say Heather is a professor, and from professor, you inherit a bunch of properties. And so by having this multiple inheritance, you have a whole slew of possibilities of bringing other information into the fold. That was question number one. So multiple inheritance is yes. And the second is something I want to show you rather than explain, is that if we go into the UKS and display BrainSim, it has a list of the active modules, and the active modules all have properties. And this is just a display. So it displays, we can see everything that it knows, including the fact that it has a dialog window and the dialog window is open and it's done an expand all, and it has the property of font size and all kinds of other things. And so when you store the UKS, you can save and restore the UKS to a file. And when it is stored, it has absolutely everything it needs in order to bring the program back to the status that it had before you started. Did that answer your question, Michael?
Almost. Do you have a list of agents running or agents with their status in that list? Absolutely.
And one of the problems that has occurred is that what used to be called what I'm now calling an agent used to be called a module. So this is a list of the active agents that are currently running. So it's running the clause window and the UKS window and the query window and the statement window. And the status is all stashed underneath that if you wanted to query it. So
okay, and also the attribute bubbling agent, is that listed as well?
No, it's not. It is not currently included. but yes, it could be. And
Okay, perfect.
it's not in this branch. This is a list of the modules that are in this branch that you could use. So we could turn on the mental model and we could turn on some other stuff. Okay, Heather, you had a question.
Well, my question was about just, the confidence, just for a moment. If you're going to start to incorporate this in a more dynamic situation, like I've seen with your robot, right, with Sally, basically you have visual input, auditory input, angle of that input relative to Sally's body center. In the brain, you would be, and also in computational models of the brain that predict very well what happens behaviorally and in the brain. You build weighting functions based through iterative experience with that visual input, for example, that visual and your body orientation input. And that weighting is very important, right?
Yes.
But what you just described for the confidence sounded like something a programmer is going to plug in. And that sounds a little scary to me.
Okay, yes, I agree. And mostly the confidence is going to be generated automatically, but we haven't gone very far down that road, except in, I can show you that in vision, where the confidence is going to show up automatically based on the level of accuracy of an image recognition, of a shape recognition.
Yeah.
And so I agree with you, that all has to come as a level of information. And another thing that I wanted that I'm not going to show you, that I'll just tell you, is that when you have exclusive properties, let's say it's not the case, but let's say that the weather cannot be sunny and rainy at the same time. And so you say the weather is sunny and you get a high confidence that the weather is sunny. But now I get input that says the weather is rainy, and that will reduce my confidence that the weather is sunny. Yeah. And so the confidence is all a balancing act. And when you search, what you do is you put in a set of attributes and you say search on this set of attributes, and you'll get a list of results coming back with confidences based on the quality of the match. And so you will get an answer based not only on the quality of the match with the query, but also the quality of the perceived accuracy of the information you got.
I see. Okay.
And I do want to say that yes, there is an issue, and one of my concerns about the way neural networks are built is that they build themselves up and they say they're storing all of this information in synapses. Well, a shortcoming or a feature of synapses is that you really can only store a single value in a synapse. But
they actually, there's also a probabilistic distribution of circuits that contribute to the synapses. And so there's never, ever in the neural circuit nor in the computational models, there's never a single synapse, meaningful single synapse. It's not meaningful usually, unless you're maybe a C. elegans, in which case there might be a specific circuit, right?
Yes, but what I want to say is that in all instances, you have not only a specific piece of information, but you also want to know the confidence that that information is correct. Yeah. So no matter what you're storing, you're never storing a single value. You're always storing multiple things. And whether or not the probabilistic question can take care of that I haven't explored.
Yeah, I mean, there's layers too, right? So there's so for not just, I'm not going to talk about your neural network layers, but just layers of what you were saying, layers of your confidence, and you're waiting for your confidence that this image is a thing, right? So for instance, in the human or in the primate mammal brain, they actually literally have columns of neurons that are representing like a head shape when it's straightforward, sideways, and this way. And literally, they can interact across those columns to understand when a head is turning, right? And they know that that's all still a head, and they can actually group it together as one. But the point is that the circuits that go into that, yes, you're right, some of them are overlapped. There'll be Gaussians of a sort in terms of synapses and input circuits that are overlapped with neighboring parts of the face as it changes its, orientation. But so there's overlap. And so that's what I meant by probability, in the sense that, but there's sometimes some of the things are highly firm in terms of you build up experience, and that image is what you consider to be a face, right? Because it has key elements of what you consider to be a face, like you said with the dog, or the other kitty cat having 4 legs, But the point is that you have some firmly established memory in those distributed synapses, if you will, or waiting in a neural network. But then you have flexible layers. You have a flexibility. And you were describing the rain versus the sun. And to me, that's a context that should have a very different weighting and a very different confidence than the confidence for an image, because the image is relatively stable in the world for some things, not everything, but some things.
Yes. And one of the things, let me answer, let me first talk about where you're talking about having multiple possibilities of image projections. That is really interesting to me, because I'm about to write that, and I'll show you the state of vision at the moment, and it's good at recognizing two-dimensional objects. But unfortunately, we don't live on two-dimensional objects, and we have to take that as and have a mechanism for projecting that into 3 dimensions. And so I'm about to write that, and that is going to be interesting as to whether you store. It is most likely, and I agree with you, it is much more likely that the mind stores half a dozen images of things in different orientations. It is much more likely that it does that than it does a whole lot of trigonometry on the 3-dimensional transformations. That seems very unlikely to me.
Yeah, are you talking about Geon library?
No. What's that?
It's what you're talking about, breaking up whatever the images are into pieces and using those pieces to represent larger objects.
Yes. Okay. Sure. And as in fact, Izzy, before we move on, Izzy, do you have a question?
No, I'm listening to this with great interest.
Okay.
I think you should follow this line of discussion. I do have questions later.
Okay.
One last thing. So the issue of confidence is interesting, because that leads, in my thinking, like confidence deals with beliefs, which is kind of a level above perception. Yasha Bach famously said, perception is just facts. Perception just is. It's neither true nor false. And so whatever we're perceiving from the perceived reality, is just factual. Now, whatever, conclusions we might infer from that, that's a matter of belief, and that's subject to confidence. I just would say that there's a difference. That's all.
Okay. Okay.
Okay, maybe I have a question that follows.
Go ahead.
Oh yeah, go on.
No, I would just I was gonna qualify that. Was that Michael that said that?
Yeah.
Sub-thought,
Yeah.
Michael.
Yeah.
Okay, so I was just gonna qualify that. I just assumed that that's what Charles meant. That he meant something that was analogous to artificial neural network weighting, which is also analogous to in a real neural network. They actually have metrics of weighting for their likelihood of being activated in a certain scenario or state. And so those things, I thought he was referring to confidence more generally as a coefficient, quite literally, to determine the upbringing, the connection between two relationships or something. But the truth is, what you're saying is a subtle factor that would need to be layered on top at another level. Because if you're interacting with the real world and you're getting real images in and real sounds in, you have to have concrete, it's not perceptual facts, right? Because we fabricate the world. If you did not know that, you need to learn that. Our brain refabricates it. We fill in missing information constantly. So like the classic example is the picket fence illusion. Like it's very easy for us, as having grown up seeing a horse behind a picket fence, to piece together all the parts and to assume that that's one horse, right? And there's geometry, like Charles was saying earlier, that also you can do trigonometry, because as the horse moves forward, parts of the horse are going in the more or less the same direction, but maybe his head bends down in each. So you have to actually assume and build that image from missing parts. Well, that basic phenomenon is true in all of the sensory systems. You're never ever getting everything in. And so you're rebuilding stuff like shadows. When you have shadows on an image, you have to make up stuff, right? You have to kind of fill in what's going on. And so that perception is not a fact, but it does require a more hard, like you're saying, I think what you meant was that it requires something that's more hardwired in a sense, in terms of that coefficient that allows you to bring together all the elements that you consider to be a face or a basketball or something like that. You see?
Is there a technical term for the filling in of these gaps, or no?
Oh yeah, that would take a little time, and I could definitely give you some information on that.
No,
Yeah.
do you just know the word? I just need to know what the word is.
Well, it depends on the context of what you're talking about, but for filling in, like in the brain, you know, it's literally overlapped, adjacent. It has to do with probability of the overlapped contours that are co-oriented. Co-oriented contours represented by two groups or columns of, early level visual cortex will literally, if they're co-oriented and you're missing a gap, then they are converging on a higher level to create that full contour that's going to be a circle or a basketball, right? And in which case, those contours, if you're missing part of it, will literally feed into the next level, and that creates the filling in, right?
But you don't have a technical term for that filling in. Okay, that's fine. Don't never mind. Move on.
Yeah, I might be able to find a technical term if people have actually come up with them in neural networks that I could give you. Yeah.
You might look into the blind spot literature too. Like that's a great example of when you kind of get this continuity error. You have filling in, and so you'll actually miss anomalous data, like if a car really is in your blind spot. That might be useful.
Well, let's move on to vision, and I'll show you a very interesting illustration of what that is. Yeah.
I feel like we touched on so many subjects. I was wondering if I could just ask a kind of a bigger picture question that kind of gets at like how all of these things are tied together. Like we talked about, like confidence and sort of like the inference, and I just feel like I want to put it together from like sensory input to like how we process confidence and how we make inference and get that to the output, because you have like explained how much the brain simulator has all of these pieces of the puzzle, right, to achieve that. So I was going to give another example. Like we talked about facial recognition, and like you can kind of think about that with the visual, but and I think we should return to that chunking thing too. That's a super interesting way of describing the problem that I think in visual neuroscience we kind of talk about it that way too. But like I just wanted a different example, I think, than the facial recognition, because facial recognition is so challenging. And I was wondering if we could like maybe imagine like more like a weather prediction, right? So if you have like changing light levels in a photo or changing cloud coverage in a satellite image, right? That's something that you could encode with the visual, like the visual recognition of the system, right? And so essentially then you have uncertainty or like low confidence because of the changing data over time, right? So this is kind of a chunking issue too, right? Like, so there's a cloud and then the clouds move to another part of the map, right? And so there's this like changing belief or changing, like a constantly updated belief of whether it's going to rain in this one spot, right? Due to, like I said, the changing light levels in an image of that like location, or the changing cloud coverage of the satellite image, or interestingly, like those two types of data combined, right? So those are two types of visual inputs that you could say, okay, I'm in the city and I'm looking at the light levels changing from my view from out the window, and I'm looking at this cloud coverage on the entire satellite image, and you're kind of putting together these two types of visual inputs. And there's this changing belief, and maybe it's like low confidence, but the clouds are like steadily moving across that satellite, the map in the satellite image, and the light levels are constantly going down, or maybe they're like shifting a little bit, maybe because the clouds are so, changing. And so then you could have varying levels of uncertainty almost. So there's got to be an inference, because essentially the desired output is it going to rain? And if it's going to rain, what time is it going to rain? Right. So I guess this is like the classic von Neumann problem. The von Neumanns, when they were building computers, right, the first thing they did was tackle the weather. And I just feel like that's always a good thing to go back to. Does that, so yeah, like how does that work in your like as an example in BrainSimIII 3?
Okay, well, let me show you this in the context of the vision, which is where I was going to go next, and it will answer a number of these questions, and then we can come back and say, perfect, did that actually answer the question, where maybe it did, maybe it didn't. And so we'll go back to this picture, and one of the things, the first thing we're going to do is change to a different file of UKS content. And in this UKS content, let's say we're going to do the vision test. And this brings up a whole different layout of agents. And the agents that are here are the vision agent, and it will work from a camera, but at the moment it works from still files for testing and development purposes. There is a shape finder that works to build a library of known shapes. And here's where it matches what it sees against its library of known shapes and develops a confidence. And here is the mental model of what the system can see internally. And I'm going to turn on a couple of these. Before we go down there, well, no, look, we'll come back to that in a minute. So giving the end-to-end of how this works, if I go to a single image, and I'll go to a square and open this file, and it says, first, in the vision system, it finds the boundaries of the square. Here's what the image actually looks like. That's the raw pixel values. It first generates boundaries, then it generates a set of segments, and I can make this bigger to just as we are looking at it. And it finds the segments, and then based on the segments, it finds the corners. And these corners have got little curved goodies in them to show first what direction the angle is that it's found, and second, because it currently cannot find arcs, and that's my precursor to be able to display arcs to get started. So based on having found the corners, it says here that this is current shape 0 because it needs to give things arbitrary names. It's a square. It has a confidence of 100%. It's a size 2. It has a color and an orientation. And here is the library of shapes that the system understands. The only shape that it knows is a square. And so no matter what it sees, it's going to see a square. And so a square is going to show up in the mental model. And the way this is stored in a biologically plausible sort of a method. Clearly, we have no idea how your mind stores images. But storing bitmaps is pretty unlikely, because as soon as you turn your head a little to the side, the bitmaps don't match up at all. And if you store the relative positions of the corners, now you can store a single object, and you can recognize it if it's at an angle. So we'll put a square in at an angle, and it says, yeah, there's a square. It's still 100% confidence, and it's at an angle, and it knows what the angle is. And so by storing the corners, you can store an object, the object boundaries, and you can recognize it regardless of where it is in your visual field and what orientation it's at or what color it is or anything like that. And so this is a pure shape finder that works by corners. Now, if I show it a rectangle, it will say it's a square, but now the confidence is only 0.75. Now, in the mental model, it sees what the eye sees until 10 seconds have elapsed, and then it reverts to saying, well, this is what I thought I saw, because it doesn't see continuously. And so let's revert and say, I'm going to refresh this rectangle, and now I'm going to say, no, it's wrong. So we'll say refresh, and I'll say, no, that's not a square. And over here, it's created a new object, a new stored shape 0, and I'm going to right click and give it a name, which is just for my convenience. So now if I refresh, I can say this is a rectangle, and its confidence is 100%. And 100% confidence is a very rare occurrence. And the only reason you get it is I'm showing exactly the same image that I just stored. So one would expect a perfect match. But in general, you don't get a perfect match. But now that I've stored that rectangle, I can see that rectangle in any orientation. And because it has the same aspect ratio, it can see that that rectangle perfectly. If I go to something more complex, we can pick up this image, and you can see that it's found a rectangle, a square, and a rectangle. And the squares, because they're squares, have perfect confidence, but the rectangles have 0.75 confidence because the aspect ratios are not the same as the ones that are stored. And so as you introduce errors into the visual field, you reduce the confidence as you're moving onwards. And we can essentially learn new patterns as much as we want, with the current exception that since it doesn't currently understand arcs, these have to be built out of straight lines. And so Another limitation is if we say here's an A, and you can see it's found all of the corners perfectly, and it's found a rectangle and a rectangle because it only knows rectangles and squares. If I put in a triangle, it will find a triangle. But it does not understand, and this is something that I can fix in the coming week here. It's an A is, in this instance, is a compound object that it is built out of an outer shape and an inner shape. And so your mind clearly has the capability of understanding holes in objects. And so an A is inconvenient in that it has a hole in it, and we have to be able to address that by saying this is a compound object and it consists of two shapes. Let's do something a little more complicated. Here's an L. I'll say that's not a rectangle. That's an L. And now it finds that that is an L. But if we, and again, because we're only storing the corners, we can see that L in any orientation we want. Here we've got it at a confidence of 92 because the errors introduced in the L are a little different. In all of this vision, there are always little errors being introduced in individual pixels. And one of the things that I learned as I wrote this is you can see all of these little errors. One of the shortcomings of, let's go back to a square because it's going to be easier to see. Here we've got some squares. You can see that if we get up the original image, boy, that's a little hard to see, that the boundary points are not in the centers of the pixels. Let's do that with a triangle, it'll be better. The key is that when you are searching for boundaries, you actually end up with an image that's a higher resolution than what you see, than what your retina is seeing. And the reason is because you see gray images. Let's turn off this layer. Oh, it's blue on blue. That's impossible to see. Let's go to a red triangle. And then I'll be done talking and can address the questions again. You can see that because of the way the image, how do you say, grays out as it approaches the boundary, you actually know where the boundary is in fractions of a pixel. And so the image in your brain can actually be a higher resolution than what your retina can actually see. And I found that I had to do that in order to get more accurate recognition. And I thought it was a very interesting result, because a whole lot of AI image recognition is based on pixel locations rather than floating point numbers. So suffice it to say, you can make any level of complexity of image and be able to recognize it pretty well. And so that, what I wanted to talk about was a little discussion about confidence and how your confidence in anything you perceive is almost never going to be 100%. And that now you see something, you make your brain makes its best guess of what that object is, and that is what you actually see. So if you can only see a limited suite of shapes, you're going to see those shapes. And so If you, for example, look at Chinese writing, you're not really going to see those characters as being meaningful unless you know it, unless you've studied it. In the same way that you know a Western alphabet, because you have spent oodles of time looking at Western alphabets. And if you look at Chinese writing, it's likely that if you look at English and you shut your eyes, you can visualize the word you just read. If you look at Chinese and you shut your eyes, you're really not going to visualize very much because you don't have the stored images. And I thought that was a really interesting result when I started building the mental model, and the mental model has to build itself out of things that it knows. Yes, Izzy.
Yeah, and that was such an interesting example, and you showed it really clearly, and I have a clear idea of how it works. I think the thing about my thought experiment was that there was this temporal element to it, right? So you had like sequential images, right, where the light was potentially changing. So I'm wondering if, as that L kind of like changes orientation, kind of the orientation stuff that Heather was talking about earlier, like, are you actually maybe getting power or confidence from just these small changes over time? And if you start to train the system on a shifting L, can it start to understand what an L really is and build that into the knowledge base a little bit better?
You bring up an outstanding point, and that is, I'm only currently working forward, where as you can recognize the L, and assuming you had a sequence of images, you can see the L moving. And so simply recognizing that you have an object moving in a static visual field is my first hurdle. But adding to that the idea that you can use these multiple images to get a better picture of the object itself, I think is a great opportunity. That as you see the object moving across your visual, if you see that the horse behind the picket fence and the horse moves, you get a much more accurate picture of the actual horse's shape.
I think that's kind of related to long-term potentiation and what Piaget would call infralogical inference, meaning that the L from one moment in time is still the same L. You know, you have to figure that out.
Yeah, another aspect of this that is completely related, and that is that this image recognition is all monodirectional. But we know that we humans see what we expect to see. And so I could easily change the system so that it, for example, if you saw two corners of a triangle, that you'd go looking for the third. And I think that's a real opportunity that is completely untapped in machine vision.
Heather, I think the last thing, Heather, I think the words were either projection or interpolation that I was looking for.
Interpolation is the mathematical operation, no question.
Mm-hmm.
Yeah. But then the other thing too is, like, going back to what Izzy said about having a natural scene, and what she said in her second comment or third comment, is that real scenes are dynamic, right? That, and the human system is divided into both a fixed high resolution, because of the physics, there's trade-offs in your ability to encode and decode basically images with high spatial resolution and orientation and shape resolution, and we do that with our central visual system. But our more peripheral visual system is actually doing the same thing with movement. It literally is inferring and determining shapes of movement, patterns of movement, and pulling out shapes. Like if you have a walking person in the corner of your eye, you will actually, you know, have an image and brain parts that that will recognize that that's a person because of its shape, but also because of its movement, because your peripheral system really there's a trade-off in physics. Like when you move fast, you can't resolve well spatially. When you're stationary, where we're reading, then you can resolve spatially very well, but you can't resolve time very well. But the point is in reality, in the real world, things are doing all those things. And so if you have a sun and the cloud is moving past the sun, you know, the sun may be a circle, but it's going to be occluded and temporarily by the cloud. So does that mean that there's no sun anymore? No, the sun's still there. You're seeing part of the sun, right? It's just partially occluded by a cloud, right? And so if you have these absolutes for like a circle is only something, you know, that has a certain like basic geometry, right? You have to know that there can be missing information and you have to fill that in a dynamic real scene. Otherwise your little robot might trip up.
Mm-hmm.
I feel like these like the questions are so like neuroscientific, right? And like the sort of getting towards natural scenes is such a challenge, right? So I'm wondering if there's like a simpler way I could phrase this, like the belief and the sort of inference sort of question with just the L, right? So is like, I don't know how you, yeah, I don't know how you'd phrase this, but like, is there a belief of the system that an L is two rectangles at a right angle to each other, or is the belief of the system that that's an L, or that is the belief of the system that an L is made up of two rectangles at right angle, or two rectangles at right angle can make up an L? Like, is there a belief that is built from an occlusion of objects? Yeah.
If you ask George Lakoff, he would say it's all of the above, because we probably store all of those associations, and all of those associations are activated at the same time, and they're kind of embedded deep. There's subconscious and conscious layers. So George Lakoff would say it's all of them.
Well,
but to get to your, go ahead.
Well, I was going to add a wrinkle to that, Izzy, that when I started doing image recognition, when I started trying to recognize test images for reading, I learned that we need to invent the concept of a stroke. That is, we don't really care that it's a rectangle. In an L is two strokes at a right angle, and an A is three strokes, which is a whole lot simpler than all of the corners that it found. And working ahead, working with strokes vastly simplifies the process of recognition. And so, and my suspicion is when you're reading, you see the strokes and you don't see the font anymore after the first, you say, oh, well, this is an interesting font, but then you don't see the serifs or anything. You say, I've got, you know, a straight stroke and a curved stroke, and that's a P or that's a D, and then and that's all your mind has to do. And I wrote a stroke finder, and it doesn't, it hasn't kept up with the boundary finder, but I think I'll be able to pull it back, and then there must be some sort of transition in your mind where you see a large font that's clearly built out of solid shapes versus a stick font that's only built out of strokes, and how you would equate those two as a bridge I haven't crossed yet.
That's so exciting. I'm wondering, so have you run this on either the stroke one or the existing sort of system that you just showed us? Have you run those on the MNIST handwriting database? Have you tested?
Well, I have gotten out a few samples from the MNIST database, which is why I know that I have to work with strokes, because the MNIST is well, let me back up and say my objective, I would be really thrilled if I could get out of the MNIST database a 70 or 80% accuracy, because I would be doing it with essentially no training. And that's what I see is the real key, is can I get reasonable results out of that? And I don't know if, for those of you who haven't looked at the MNIST test data, there are many letters. It's digits 0 to 9, and if you weren't told that it was only digits 0 to 9, you'd have no way of knowing what these digits are. And many of them. As an example, there is a 7 that's built on an angle and it goes up and down. And there's a 1 that for all the world is identical to the 7. And yet somehow you're supposed to be able to intuit that one of these is a 1 and one of these is a 7. And so that's why I would be thrilled with, anything above 50% accuracy in MNIST would be outstanding.
Yeah, it's such a challenge. That's really cool that you're thinking about it and working towards that. That's awesome. Yeah. I actually have to take off, but this has been amazing. I'm so eager to jump in and have a great discussion next time. Does it usually last like an hour, 2 hours? Is it just kind of an ongoing discussion?
I usually shoot for an hour, but clearly we had at least 2 hours of material this week. I'm so cool. So glad you could join, and I look forward to also having a conversation with you on the material that you brought up in your field of expertise too.
This is great. Okay. And I look forward to many further discussions. Bye, everybody.
Bye.
Have a great day. Bye.
Heather, you had your hand up.
Yeah, I was only going to say one thing, that I don't want to deviate because we're talking about vision and everything, because I think vision has been worked out. Computer vision is very well worked out. Strategies for how to make it work. The interesting thing is when you get into audition, some of the problems that you've been talking about are also there. With speech, it's a little special because your brain does a lot of predictive coding based on actual motor movements. So you represent all of your speech phonemes through like ma, ba, da, ga, or if you're Chinese and Mandarin, then, ma, ma, ma. So you have very different kinds of representations of speech in different languages, but in English that I'm more familiar with, basically people have, looked at it, and the brain is very much using the motor representation, and it's reciprocally connected with the audio representation for you to allow for a predictive match and coding of what's coming up. You predict what's going to be immediately coming up for a phoneme change or a syllable change, and you and then you basically confirm that. If it doesn't surprise you, like if it doesn't go in a different direction, then basically your comprehension is to group it as this one acoustic object. Oh, she said mama, right? And so basically, then you're confident. And the network is active, and it has that meaning associated with what you just heard. However, if there's a deviation from it, yeah, sure, there'll be, they can fill it in many different ways. But I'm just saying that we won't go there today, but that's going to be another level of complexity. And like when you were saying with written letters, visual letters, that I've not studied. I've studied more, other kinds of visual systems and computationally modeled them. That is an abstract thing to basically categorize cursive L and the, basically other kinds of L's that you might see as to be all one, right? Right. And that is a level of complexity that's going to be hard. And you could, in theory, encode it, like you said, with how you make it, the strokes, the orthogonal strokes. But I don't know that field. So I don't know, and to be honest with you, what's been done. Usually in image computer vision, it's really just they've learned through many images, right?
Yes.
Can make mistakes.
Well, let me give you something that it's kind of interesting that you know. By the way, I wanted to say that you know, if you can only recognize squares, that everything looks like a square. It's like if you only have one, if you only know how to write software, everything looks like a software problem. And but it's kind of interesting because from my perspective, speech recognition is miles ahead of vision. And I think particularly when I go to, and I keep falling back to this, the speech recognition on Google search is outstanding because because clearly they have a pretty good idea what you're going to say based on trillions of data elements, whereas an arbitrary image could be almost anything. And only after you've seen the arbitrary image can you make some prediction of what the next arbitrary image is likely to be. Yeah.
But they get that wrong sometimes, though.
Yes, they do. And so in my humble opinion, that one of the things that's really holding self-driving back is that vision doesn't really work very well. And so you're left with all of these shortcuts and coping mechanisms like LiDAR and radar and acoustics and all this other stuff to cope with the fact that the vision is garbage. And I would add to that that the very first phases of image recognition don't work very well. And then you spend the rest of the 9 layers of neural network trying to cope with the fact that you didn't really do a very good process of boundary recognition or corner recognition, and you're having to recover from that by other levels in the neural network that no one really quite understands, I don't think.
Yeah.
And so one of the things that I did over the past month is I discarded a few thousand lines of code that used some classic algorithms for boundary detection. And I wrote this homebrew thing that in the instances I have given it works much better. May not work as well in real world images, but and it also suffers a little bit from being ponderously slow. And has anyone here used a quad tree for spatial stuff?
Yes, in the past, a long time ago.
Oh, was it painless or painful?
Depends on how you're coding and what you want to represent. Could be painless.
Oh, I was going to use somebody's library, but but I hadn't looked. If you had a recommendation on a library, I'd be interested. But my suspicion is that with a quad tree, I can make all of my performance problems go away. And as I mentioned earlier, one of the issues is that since I'm storing all of my boundaries now as fractions, the number of being able to search just a small area and just get back the boundaries that we have is really important. So, hi, Fry. I just wanted to see that you joined. You're muted, but that's okay.
I think Fry's having trouble locating the unmute button.
I see some quad tree libraries on GitHub, so there might be.
Yeah. So, hey,
there's also,
sometimes you see an article about a library that's going to solve your problem and it works, and sometimes you see it and it's just a can of worms.
Yes, and so you want to make sure that you don't waste your time. I understand.
Right.
Yeah. So, yeah, so this was good. I'm looking forward to more on the visual.
Vision.
As a
But
good
now
start.
to the extent that people have time, I really want to talk about language and ambiguity. And so,
Charles,
yes.
I figured out how to unmute myself. That's a common sense problem. I have
Okay,
a,
good.
I'm sorry I'm late. I have a
We're glad you're here.
comment about your vision stuff and saying that vision is out of context. First of all, you intimated that Google search knows what you're going to search for and therefore can predict the words. Well, maybe, but I'm using Google speech recognition and Chrome browser for all kinds of stuff, not just search, and it works really great. And we can predict things. But on the vision stuff, I think we can also predict things, because when you see a scene, you know you're in a house or you're in a kitchen, and you know there's kitchenware, you know, and drawers and cabinets and stuff. But if you see like a submarine in a kitchen, you go, well, what the heck is that? You're confused. Now, on context, I think we can use the UKS, because the UKS will know what's in a kitchen. And if you know you're in a kitchen and then you see something that sort of looks like a submarine, you're saying, wait a minute, that can't be here because submarines are only underwater. Maybe it's a cucumber, let's say. And so I think there can be a play where the UKS and common sense can help guide where to direct your vision, and that can help improve accuracy, just like prediction of sequence of English words.
Exactly, and that was the point where I was saying that the vision system I've written is one directional, and it doesn't take advantage of the fact that it's got all of this information in the UKS that it could be using to enhance the recognition. That and my example was, if you see two 60-degree angles from a triangle, can you look for the third? And either it's going to be there, or you're going to say, oh, there's an occluding object, or maybe it wasn't a triangle after all. And that's an entirely new direction that I haven't addressed before. I think that's going to be really fascinating.
And you said that you have defined boundary conditions for simple geometry, but you could also define boundary conditions in the same way Fry was just saying, in the sense that context, in a sense.
Yes.
Yeah.
And the truth is you might still have a submarine in the kitchen. It might be a toy. So
well,
you know.
And another problem I have to address is that I've got a system that works pretty well on straight lines and angles and corners, but in the real world, almost everything is a curve. And so the fundamental the fundamental primitive is going to be an arc, and a straight line is a special case of an arc with no curvature, rather than trying to make an arc a special case of a line. And fundamentally, the system has to work entirely in terms of arcs and rounded things and fuzzy edges.
So Heather, you brought up an important concept, which is context recognition. So when we see a picture of a kitchen, how do we know it's a kitchen? Well, because it's got, you know, part of a kitchen is a sink and a counter and all this stuff. And so if we can use the things that we do identify fairly easily and then map it into the UKS and say, okay, what are these things that we do see part of? Then we can say, oh, we're in a kitchen, and now we've got context recognition, and now we've effectively switched context and can focus on that context. I don't hear anybody in machine vision talk about context recognition.
No.
Fry, this is Mike. So I listen. I'm doing a another video on grounding, and part of grounding, it talks about perception, activation, and association. And I listened to a couple people. I actually talked to Charles, and I'm fusing a lot of what they all said. So George, the main influences are George Lakoff, Roland Hauser, and a couple other people. On the notion of context, so George Lakoff, at the highest, we have to look at two things. One thing is long-term potentiation in the brain. That's where the brain starts making connections between whatever's going on in the short term and whatever's going on, you know, like over a period of hours or over a period of days. And I suspect that from long-term potentiation, we get, you know, place cells, you know, you know, like locations, specific locations, and we also get specific events. And to tie it together, George Lakoff, he talks about the notion of frames. And a frame is basically a generalized episode where in the frame you have scenarios, which are individual episodes, and you have roles, right, which are the actors that are in the scenarios. And so this from the top, that goes from the top going down. Then you have from the bottom going up. Bottom up is perception. You know, what's going on, perception, moment to moment, instant to instant. And there's a convergence between, you know, the top down frames and the bottom up perceptions. And there's a whole lot of things going on in the middle. And what goes on in the middle is a lot of activation. So what you're perceptually seeing in a particular scene and the objects that you identify in the scene. So we're talking about a kitchen, being in a kitchen. We're talking about seeing different things. Potentially one might be a submarine and so on. And you have all of these things bubbling up, or not necessarily bubbling, but you know, they have different activations, and the activations are crisscrossing. Some of them are coherent and some of them are incoherent. So the coherent activations would be seeing objects that you identify as things that belong in a kitchen. And then the things that are incoherent are seeing objects such as a submarine that do not belong in a kitchen, that probably activate a different set of frames. And it's a matter of, you know, saying, okay, what is the probability? What are these probabilities of these frames being relevant versus other frames being relevant? And then, you know, you have the expectations that are driven by these frames from a top-down perspective, and you have the current situation, current activation being driven bottom up from your you know, your observed reality. And so there's kind of, you know, I was taking into account what Heather was talking about with the projection and interpolation of reality not being totally factual, as you know, she reprimanded me about, but it is a matter of not hallucination, but it's a matter of
belief.
How would you say it? So reality is not totally what you perceive, it's what you also project. It's a balance or a dance between projection, what you're expecting, and also, you know, and filling in the gaps versus what you are perceiving. So I don't know what you call that. I have to get a label for that.
People usually just say, if you want to be agnostic, you would just say representation. How it's represented in your mind. And that can be both top down and bottom up. But the bottom line is what you're saying, the beliefs or confidence and all that stuff, it can be a complex process of both. Right?
Yeah, it's an interplay.
Oh yeah, that's true for everything. True for everything. Like for instance, for speech, it's really important in speech. Yeah.
Mm-hmm.
And I agree that, Charles, that Google voice recognition is largely accurate, but for me, because I have all these esoteric words and phrases like infralogical. They never get that right. They never get that right. And infralogical, from what Piaget says, is infralogical just means that from moment to moment, you're trying to identify that something is the same thing. And they don't even have that definition in the dictionary. So.
Yeah. I get the daily comparison because I have the Amazon Echo device that I won't use the name of in the house, and its speech recognition is nowhere near as good as Google's. So, by the way, in talking about this context and using the content of the UKS to understand better what it is you're actually receiving as input, that's something that's really going to be important in language. And that's a great segue to get to the project that William's been working on that he asked me to demo, but it now has the ability to go to GPT and get multiple meanings of words and create a data structure that differentiates the multiple meanings. And I'm going to walk through this as a demo of what the UKS content looks like, and then we'll discuss on the other side here. So this is in yet a third file called, oops. If I pick it off of here, I can pick it off the recent list. Disambiguity. And here we have some UKS content, and this is getting to be larger, so we're going to be not showing the whole UKS the way I did in the first demo. But if we see, we have an apple and an apple 0, which I can right click and see what the parents are at the bottom of this pop-up. So that apple is a fruit, and this apple is a tech company, and this apple is a tree. And let's do a couple of more, and then we'll go to the words. Here's a pen. This pen is a writing tool, and this pen is an ink container, and this pen is an animal enclosure. And the last one I'm going to bring up here because it's fun. Here's a tank. And a tank is a container, or a tank is a military vehicle, or a tank is a fish habitat.
Unknown caller.
Sorry.
Oh, okay.
Turn my mic off.
And
so Charles, yes. Those are not mutually exclusive. Like a
not
fish container, an aquarium is a container. So you have to be careful with the relationship.
Exactly. So the way this was built is out of a word list. And let me show you the word list to give you an idea of what's on it. I found this list of first grade nouns every child should know.
Good.
And there are about 100. And I've also got kindergarten nouns and second grade nouns and third grade nouns. And we stuck with nouns because they're a whole lot more useful from a UKS perspective. So now these are words, and I've prefixed them with dots, which I agree with you, Fry, is not my favorite idea.
It's a hacker thing to do.
Exactly. And the problem I have to get around is that node or thing labels have to be unique. And so if I want to have a thing which is the fundamental concept of an apple, I have to differentiate with the word, and I could prefix it with EW for English word or something or other like that.
Yeah.
But the words are separate from the objects themselves.
Yes.
And that was not helpful. But I can see the relationship where apple means apple 1 or apple means apple 4.
Mm-hmm.
If I go to tank, just so we get the ones. Wow, tank is down here a little further than I thought. There we go. So it's a tank 1 or a tank 0 or a tank 2. We can right click now on the relationship and go to either the source, the target, or the type. And so this is a tank 0, and a tank 0 is a container. And I should say I've added a quick search here, so we can go back to words. And we've made some performance improvements so that, by the way, William wrote a little stress test program, and the system immediately fell over with about 10,000 nodes. But it falls over not because of the UKS, but because the tree control in this display is very unhappy with large amounts of data. And so we had to add a few goodies to keep the amount of data in any particular node down. And one of the things that the subclassing agent will be able to do for us is, here we have 100 children of the word item, but it should be able to build intermediate clusters of words automatically, so that you never get, say, more than 10 children on an individual item. And that will dramatically improve the performance of this tree. Yeah,
for display purposes, you might just want to add ellipsis nodes, and display and grab like 50 nodes, and then have an ellipsis node in the middle. And if they click on that node, then you go and fetch the data that you really need.
Yeah, well, ellipses themselves are really easy, but then getting the rest of the stuff is a beast. But it is a possibility. And I don't know if you've used this tree control, but it does not lend itself to large data structures, which is kind of peculiar.
Yeah,
because
you have
one
to,
would hope. Yeah.
You
One
have
would
to
hope
page
that
through stuff.
Yeah, that you could have a tree control that was, for example, the entire disk directory structure on your computer, but you can't. So anyhow, that's the structure. And William was currently working on building a dialog box that makes all of this stuff a lot more entertaining, that you can, for example, put in a set of words, try and figure out what is the appropriate context, and then output something useful back into the dialog box. And that I thought would be an interesting module to add to this. But we're just at the very beginning, and we've just got a small number of words. And I think that the prospects are really interesting in a number of ways. The first is you can represent these multiple meanings. The second is that you can go to GPT as an engine to get the multiple meanings for you, and get them back in a format that you can stuff into the UKS without ridiculous amounts of effort.
Have you looked at WordNet already, or no?
Yes, we looked at WordNet. What did you, William? You looked at WordNet, right? He's nodding.
What did you get out of it? Because WordNet is basically what you're doing as far as synonym sets and differentiating different meanings of words that have the same, I forgot what they're called. When you have a word but it has different
Synset.
meanings. No.
Synset.
Synset is the opposite. Synset is different words that have the same meaning, but a word that
Oh,
has different meaning, there's another word for that. I forgot what that's called.
well, polysemous is,
Yeah, polysemy or something like that.
yeah.
Well, what I got back from it is that the results tend to come back in English and then have to be parsed, where you can coerce GPT into giving you one-word answers for the most part. And WordNet didn't want to do that, at least in the samples we pursued. Anyhow, so yeah, we tried it and we thought that GPT was easier because it was easier to force into giving us an answer in the format we wanted that was easier to plug in, not because the quality of the data was particularly any better.
Right, but what WordNet gives you is a list of distinct meanings.
Mm-hmm.
And yeah, distinct meaning. Each synonym set is a distinct meaning, and then those other the members of the synonym set are the elements of the synonym set are variants of that particular meaning.
So what do you think, William? Is that something that you want to pursue?
I could look into it more.
Sure.
Because it seems to have better results than GPT at times.
Mm-hmm.
Know what I mean?
Yeah.
I'm almost 100% sure that GPT has been trained on WordNet. So I think the interesting question is not, whether GPT has seen WordNet, is whether it gets it accurately. Just like GPT with everything else. Yeah, so that's really the catch here. But
maybe you could prompt engineer GPT to restrict its response to data from WordNet. If you just like the interface, the I/O GPT, there's a possibility of doing that.
I bet
that's an interesting idea.
Yeah, I bet if you prompt GPT to output the entire WordNet, it could do something like that. given the context window fits and all that, right? Yeah.
Only for Apple. Only for the word Apple. So the one thing that I thought was I listened to this lecture by George Lakoff. He wrote several books, but the interesting thing about him, he talked about image schemas as well. So image schemas are they're schemas that we have that are like fundamental to our language. He talked about like into as a compound word. We think of it as just a individual preposition, but he says it's made out of two schemas. One schema in, which has basically a container, a boundary, and a container, and one other thing, I forgot what that was, and two, which is source, path, destination. And it's a combination of those two schemas actually. So kind of two things are happening at one time. When you think about into, you're thinking about being inside, and you're also thinking about motion toward. And so his whole thing was that language is all about activation and ambiguity. You can't get away from it. That's the whole purpose of language. We can't disambiguate it. And it's at a micro level, not at a macro level of definition of words. It's subword.
Subword. I did do very brief experiments in asking GPT to identify compound words, and it was reasonably successful in determining compounds that were what I don't remember the verbiage for it, but compounds that are shoved together into one word, like into, as you brought up, those that are hyphenated, and those that are completely separate, like tennis ball. Well, tennis ball is a single thing, and isolating the two words doesn't particularly help. But from a UKS perspective, tennis ball has to be a single node, and it happens to be represented by this compound word that means tennis ball.
Also, what about metonyms? So metonym, like Bigfoot is a metonym, right? Bigfoot, if you look, it's the foot, it's a part that represents the whole thing. So, you know, Lakoff gets into that too.
Okay.
Metonyms and metaphors, yeah.
Is that a book that's worth reading?
No, it's a video that's worth watching. He has a good video. He has several good videos on it. They're about an hour each.
Great. Could you send a link?
I don't have any links.
I guess you can't because you're driving.
He's famous. You can find it.
Yeah. George Lakoff, yeah.
Brian, you had a bunch of really interesting observations in your email over the last couple of days.
Thank you.
Where's a good place to start?
Well, I don't know, but you mentioned doing something about getting word meanings out of GPT. Are you using embeddings? This is maybe a question for William.
Yeah.
Oh, we haven't used embeddings yet, but that could be used, yeah.
Yeah, it's just a definitive way to do it. And what I like about embeddings is a vector of numbers that tells you kind of what the meaning is. But what I use them for in my environment was you have to explicitly ask for embedding. And you can ask for an embedding of any phrase. It can be a single word or a phrase or a whole paragraph. And then you can do a math operation of comparing those two vectors and see how similar they are to each other. And then you get a number, it's like a 0 to 1 number of similarity. And then, as I mentioned to you, Charles, similarity and between have a important relationship between them. The similarity in between are similar in a bunch of ways, and they may help with figuring out how to compute betweenness.
Mm-hmm.
Now, the UKS itself has important ways that you can do similarity, like basically how many hops away is one thing from another. Just that. What's the shortest path from this thing? Shortest path from this thing to that thing. And and that's a great that's kind of like correlation in a sense, but I think it's related to similarity. It's an interesting metric. Just like, I was saying my email, you go up and look at the ancestors and you see, we can do this sort of betweenness on any tree, as you noted, right? That's a great thing to do. But then what's an uncle? Well, it's not really between you and your parents, but it's in the neighborhood is the thing. And so that's where kind of similarity comes in. An uncle is similar to your parent. And
is between intersection? What do you mean by between?
Two concepts. The deepest thing is the meaning of something and the meaning of something else. Like lifeboat and lifesaver. Or is life between boat and saber, or those kind of weird, complicated things that humans do with analogies.
Yeah, but what might a 3-year-old do?
I think they do spatial stuff.
Yeah.
That's the simplest one, is spatial. And you brought up in your latest post to me, Charles, you brought up spatial betweenness, and you're sort of like shunning away from numbers, but maybe we can find a way to get numbers in there anyway, because they are useful. But if you imagine that you're looking at a painting, you might overlay on the painting a grid mentally. And the very least, there's the upper left, the lower left, the upper right, the lower right, right? And so you've got a 2x2 grid on that painting. And then you might do a nine, right? Center top, center bottom, center left, center. So a 9 grid is, and I think people do this. I mean, I know that I do, but maybe that's because I'm such a nerd. But a 9 grid over something for spatial recognition, and then you can number the elements of the grid. You can say, well, if it's diagonal corners, then that's the furthest apart you can be, and they're adjacent. And so, I don't know.
Mm-hmm.
Yeah, like let's take the 9 grid. Okay, the furthest apart you can be is one corner diagonally opposite the other corner. Then the next is one corner on the top left and one corner on the bottom left, right? And then you can be adjacent, and then you can be diagonally adjacent, which is a little further than rectilinear adjacent. So we get all these distances from our 9 cell grid that seem pretty normal, because we have terms for top center and bottom center. They're not that uncommon, so they're concept. And then of course you can say, okay, what if we put a 9 grid inside one of the cells of another 9 grid? And now we can build up this hierarchy of grids with this notion of 9 grid resolution, kind of. The next level down is a 9. And going from 1 to 9 is a kind of a nice level of detail jump, I guess. It's not a million,
Yeah. Well, directly related is, what do you suppose is the resolution of your mental model? And my
it probably
suspicion
varies.
is,
doesn't it vary with context, or I don't know what?
Well, certainly, if you think about what's, the objects that are on the wall behind you, you have only a vague idea of their relative positions. But the objects that are in front of you, you have excellent perception of their positions relative to one another, and only vague ideas of their absolute positions. So, for example, if you have my 3 pictures analogy, you may only be able, if you got 3 pictures in a row.
Yes.
And they're not spaced evenly.
Okay.
You may or may not be able to tell what the spacing is between them, but you can easily tell that this space is larger than that space.
Yes. But that's okay. That's just estimating and stuff. And I mean, I find that people that think carefully are better at estimating than people who don't. People are good at generalization, are good at estimating, whereas a lot of people, they say, well, what's 99 times 101? And they, well, I don't know, I got to pull out my calendar. Well, I just say it's the same as 100 squared. And then, is it exactly right? I don't know, but it's pretty close.
Yeah.
So but on the resolution, let's say you're walking down the street and you see a bunch of houses. Okay, I see like 10 houses on the street. But then you have no problem of going into one of those houses and saying, yeah, this house has about 10 rooms in it. And you have no problem going into the kitchen and seeing that it doesn't have a submarine and, has knives and stuff in it. So we change our resolution of what's in our frame, to borrow a term from our friend here, Michael. Again, frame and context, I think, are about the same thing, right, Michael?
Yeah, well, no. Context is like your immediate situation. Frame is a technical term that Lakoff has kind of coined for himself, but that's okay. You can leave
but
Lakoff with that word.
your current situation could be a frame amongst a zillion frames. That's all I'm really saying. So, but any case, I think to go back to Charles's point, your resolution changes based on what you're focused on, but we know your mind knows that a can of tuna fish can be in a kitchen when it's walking down the street looking at the houses, but you're not thinking of tuna fish until you get into that frame, and then you focus your mind on that frame or that context, and now tuna fish is normal.
Can I propose something? Can I get your feedback on something? This is relevant.
You're going to make a proposal. Okay, are you down on one knee?
No, I'm sitting on my
Speaking
butt.
of language and context. Okay, go ahead.
Okay, so I'm proposing a naive perceptual system for a robot, right? I'm using the Now robot as a reference. And we'll talk about the visual system for the robot. So the robot has cameras, it has microphones, whatever. But as far as the cameras are concerned, we have two cameras that are recording video at 24 frames per second. Let's say 24 to 30 frames per second. So it gets a video clip and then it stores the video clip in some on Internet Archive. But it gives us a handle, it gives us a URL to the video clip. And it's doing this every 3 seconds. So these are 3-second clips that we're getting URLs or handles to. Now, I wanted to create a naive perception system. And a naive perception system is going to do a couple things. One, it's going to take a frame from the video clip, just one image, and it's going to divide the frame into a central fovea area.
Good.
Some percentage of the front, and a scene, a peripheral scene area, some percentage of the back. Then I'm just going to, for the peripheral scene area, I'm going to cut out the middle and just do a hash of that scene and store that hash number, long hash number, a GUID could be, hash it into a GUID or something, but just store that hash number as an identifier, right? So now I have an ID for the background. And for the front, I'm going to identify as quickly as possible as many shapes as I can in the foveal central area. And whatever those shapes are, I'm going to take those shapes and save them. If they don't exist, I will store them and then just get some IDs back for these shapes. So this is my naive.
And is the operation, what is this picture about? Oh, you look at the center of the picture and there's a cat there, so it's about a cat, even though there's a dog to the lower left.
Well, we're just saying this is the current scene. This is the current scenario. We have a background and we have a foreground with some shapes in it, and that's it. And that's our naive perceptual system. And the naive perceptual system, over time, it will store, it tries to match the scene and it tries to match the shape. So it will do an 80% match. If a shape is within 80% of something it's seen before, then it'll retrieve what it saw before. If the scene is 80% of what it's seen before, it'll retrieve the same scene as the ID. But if it's like less than an 80% match, then it'll store whatever the current scene, whatever the current shape is, and it'll restore the current scene. So the scenes will change over time, and the shapes that are in the fovea will change over time, but it won't change. It'll change over time. But what we're trying to do is we're trying to establish some consistency and regularity in what we're seeing. And these things are all, they have no labels attached to them. They just have IDs coming back. And then if we want to ascribe a label to it, like a cat or a dog or whatever, then we will ascribe those labels. We'll attach other labels to these items. So what do you think about that naive perceptual system?
You know, while you were talking, I kept thinking of, oh, if you'd use my 3x3 grid, the center one is the fovea and the 8 surrounding are the scene. And then you shift it over one, and it's just a real cheap way to get a fovea is just that center square, right? But then that also has the advantage of the adjacency of all these other things and embedded 3x3s, and it's almost a computational cheap trick, because the eye is probably much more like a center circle or a bullseye than this, but you know, this is like more modular, and then you have all these little 9 pictures, you know, and they're adjacent to some other 9, you know, that shifted over.
But I would coalesce all those 9 pictures with the hole in the middle, and I would just calculate that as a store it away as one image. But
well, I wouldn't. Yeah, it's both one image and 9 images. That's the thing, right? Right. Could be the same pixels with just different boundaries or something. I don't know. Right. I'm almost thinking of, this is a little going on a stretch, where you're thinking about panoramic views, and imagine your mind, all it saw was one giant panorama. It only had one picture in it, only one. But then at any given time, you're just looking at a particular one. And it might be because, you know, I live in Boston. I go to visit you in LA, like I didn't do, right? But for me, Boston and LA are kind of more closer to each other than either one of them is with St. Louis. Because St. Louis, that's like outer space, you know, but Boston and LA, oh yeah, there's a, you know, and so we have this kind of funny, warped, giant one picture in our mind with these adjacencies, and I want to adopt a little bit of Charles's, like, adjacency stuff is more important than actual physical, you know, Boston is 3,000.7 miles from LA kind of thing.
Okay. So the whole idea is that we would abstract away whatever we saw and instead retrieve identifiers, retrieve IDs for all of these different shapes or all of these different scenes. And if a scene matched a scene that we've seen before, we'd say it's that other scene. But if it's something completely new or largely new, you would say, okay, this is a new scene. And so we'd have some library of scenes and some library of foveated shapes. And we'd, you know, use that as our, then the next level gets in as our, the next level is SLAM, which is, you know, like bringing out, retrieving maps and also retrieving our location in the map. But we'd have a whole host of different maps, and we'd have a whole host of different locations.
Use the term content addressable memory. I think that's what you're really talking about here, right?
Yes, absolutely.
Good.
Yeah, so that's just the naive thing. And then we could do the same for audio, but that's a different story. Anyway, what's your opinion of that, both of you? And then, well, I guess we have to run.
Yeah. First, that's the direction I'm going. That what I'm currently doing now is taking my scene and plopping the objects I recognize into a mental model. And then I need a mechanism for storing a mental model as a situation and then recognizing situations when they recur. And I think that's a large piece of what you're suggesting.
Yes. Yes. And okay, so the
And I think I mostly have all that code already existing. That
excellent.
because that and although it's completely untried and unwritten, if I have the code that already puts things into the mental model, now I already have code that will take a snapshot of that mental model and store it somewhere, and I already have code that will do closest match searches to see if, given a whole slew of saved content, which one is it most like?
So okay, so here's the next piece of that, the next level of that, right? That's the perceptual level, and
Right.
and so what we are retrieving are features of the current percepts, the current visual percepts or the current audio percepts. These are features, right? Now the next level is binding those features, right? To say that this is a context now. So the level after that would be to synthesize new objects that bind all of these features that we've just extracted, that we've just detected. We bind them, and then we bind them within the same modality, and then we bind them across modalities so that we can get entities, and then we can get events as these features come or go over time. We will be able to say, okay, this set of features was here, now it's a new set of features. Now we have events, which is another binding on top of that.
Another thing that I think that I will be able to do pretty easily is to say, this situation is just like that situation, except. So this is the situation of being in the kitchen, and this is the kitchen that I currently see that has a submarine. And then I will have my attention drawn to the submarine.
Because you look at exceptions. We like exceptions. I wanted to say something else here. What if we consider a color to be a picture that's just one pixel? Okay. And then what if we consider a shape like a triangle to be a picture of a triangle? And now let's say you have two pictures of triangles stored in your mind's eye, I'm guessing, right? And now if you want to say, hey, is this picture like this other picture? And then Charles, what you're talking about, I think maybe both of you, is we do almost like an image recognition thing to see whether these two pictures have, and we might be able to bias our similarity on the dimension of color or number of lines or something like that. I don't know. But if this, the pictures were the picture view of the entire world, like a Pictionary, the definition of this thing is a picture, not a bunch of words. I'm just playing here, but mostly I think about words, but the pictures might be better for 3-year-olds.
Right. So the whole idea for me is that we have these perceptual streams coming in, which we chop into individual percepts, which are, segments of these streams, whether video or audio, or just kinesthetic joint positions at a specific point in time. So we are sending all of this stuff into this sensorium, right? So all these percepts are coming in. And then we have detectors, and the detectors are mechanisms that take each stream and extract what it can, right? Whether triangles, whether just shapes, color, or whatever, color, whatever. They extract whatever they can, and then they assert to the UKS, or to the database, at this particular time, I experienced this particular feature.
Good.
And then it's up to and that feature gets activated, meaning it gets timestamped.
Yes.
Then it's up to associators, which is another grouping of mechanisms to say, okay, let's look at the memory and let's see what we've had. Oh, okay, we see that these particular features occurred at this particular time. Let's group those particular features within this modality in unison together into a group. And then, let's just basically have these different mechanisms that do different kinds of groupings until you get to the situation group, and then until you get to the event group or whatever. And it's all about, just grouping these things and activating them at particular times.
I think a problem, a problem I want to add to that is that at each level of this storage, I want to be able to extract the things that I think are important. So I'm not storing the entire scene. I'm only storing the pieces of the scene that I think are important, or the pieces of the situation, or the pieces of the phrase, or what have you. Because
that's why we have the fovea. That's why we have the fovea #1. So we limit how many features we generate.
Oh yeah.
And then that's also, then you're going to have to say, okay, why is something important? You're going to have to figure that out. Well, why is something important? Is it just because it's different?
I mean, that's, and if I have a picture of a lake, the fact that there's a tiger in the back of the picture is not related to the picture of the lake. And I want to be able to recognize similar situations either with or without the tiger. So the presence of the tiger is the unimportant thing to remember, or the important thing to remember.
Okay, now so novelty is only seeing something that's different from what we've experienced before, and the novelty is so novelty detection is something that probably we want to have.
I like that word.
Yeah. So basically, we're taking in, these scenes, these words, these phrases, whatever, and eventually associating everything up into a situation. And then we have situation to situation, moment to moment. And maybe it's the case that for 10 frames, it's the same situation. So we don't have to store anything new. We're just retrieving back what we've already seen and reactivating it, right? If we've already seen this stuff, we don't need to create anything new. We've already seen it. So it might be slightly larger or slightly smaller. That's a matter of the trajectory detectors or whatever. There should be some kind of translation for. So we have different kinds of detectors, but a basic shape detector and a basic whatever. Again, the word geons is for 3 dimensions. Shape is for 2 dimensions, right? So we can have a 2-dimensional shape detector that detects things based on, size. It could be small or large. Translation, we don't care. If we have a trajectory detector, that's a different thing. That trajectory detector, based on the size of something, will say if it's moving in a particular direction or whatever. But essentially just a simple shape detector, a simple background scene detector to see if we've seen this background before. And we can go from there. And then we build up these internal associations. And then these associations will be activated. And, so that's the entire naive perceptual system that I'm going to describe in this next video.
Okay. Do both of you guys like to think about episodic memory?
Yes.
So the way I'm picturing it now is you've got this, a film camera, a video camera, and you're taking snapshots every second, and you're time stamping those snapshots, and they're going in a sequence. And then when you see a tiger, you could map it to, oh yes, I saw a tiger last year when I was in India. And then you activate that India context and you can see I don't know, Indian restaurant you went to that was near the tiger or something. There's those kind of associations via time, just association with their time. And that seems pretty powerful, but also really simple. What's correlated with what? Well, did I see it at the same time or close to the same time that I saw this other thing?
Well, so when you see the tiger, right? Let's say there's a tiger in a lake, right? So first you have this scene of lake, and then all of a sudden a tiger jumps into the lake, right? Now you have this tiger. And the question is, what do you have? What are the associations you have connected to this tiger, right? You talked about an Indian restaurant or whatever, and seeing a picture of a tiger in an Indian restaurant. So what I can see happening is that from that image of the tiger, it gets a key point as well for this whole naive perceptual system is that the shapes correspond to a handle or to a number, right? The scenes correspond to a handle or a number as well, a different number. And so even the word tiger, whatever, it corresponds to a handle or a number. And it's all we have really are these handles and the timestamps that these handles, and then any associations between this handle and some other handle, we have these activations. So the activation can be propagated from whatever's in the current scene, whatever the current handles are, to other handles. Does that make sense?
Oh, yes. And let's introduce the word place stamp. Timestamp puts a time, and so that previously and next and all that. Place stamp will say, oh yeah, this thing was placed next to this other thing. And ultimately I suppose it could be a Latin long, but
Yes.
we can do relative, whatever we like here on our place stamp.
Yeah.
So that's the key. And the place is the background, the hash of the background scenario. It's that all those other 8 cells in your grid, we hash that out to a unique ID. And then that ID, so that ID becomes a particular scene. However, the scene occurs within the episode, and the episode occurs in one or more places. What do you think about that?
Yeah, okay. Yeah, I was a little nervous about associating the can of tuna in the kitchen with the whole kitchen. I was more just thinking about the can is resting on the countertop. And so those two place stamps are very similar to each other. I mean, we should be able to compare the two place stamps and see similarity, close to each other, just like two timestamps are close to each other because they're within 5 seconds of each other.
I didn't even get into temporal juxtaposition. I didn't even think about that.
Another thing I'd like to expand your idea on the episodic memory to think that there's no particular reason that the episodes are continuous or periodic, that you only remember the episode if it has something interesting in it. And now we need some sort of mechanism for knowing that this one, that the gap between these two was a couple of seconds and the gap between these two was a couple of hours.
It's the between.
Yeah, agreed.
Yeah.
The intersection of the
More
elements.
betweenness.
Charles, I'm going to coin another word here, which is preemptive garbage collection. It sounds like you're saying as it's coming in, oh, we've seen this before, throw it out. But when we throw it out, we're going to add a little uptick to the original to say we've seen it.
We saw that one again.
Isn't that
The
true?
usage count. It's the usage count. The ref count or the usage count.
Yeah.
Hey guys, on that happy note, this has been a really fascinating conversation, and I want to thank you, and I want to thank the people that already left because they ran out of time.
Yes, let's thank them.